Hello, my name is Chef Peeters. I work for the University of Leuven and I will present you the main results of the article Closed Loop Recycling of Plastics Containing Flame Retardants. In total, 2.7 million tons of plastics containing flame retardants has been calculated to be annually discarded in waste of electric and electronic equipment, which is a considerable amount when taking into account that this equals a business potential of about 8 billion euro and a potential CO2 reduction of up to 8 million tons of CO2 per year. The presented research focuses on recycling plastics containing flame retardants from LCD TVs, since end-of-life LCD TVs are separately collected, and approximately 1 million LCD TVs are forecasted to be discarded in 2015. Another reason why the presented research focuses on LCD TVs is because LCD TVs contain a substantial amount of plastics, of which on average 35% contains flame retardants. To recycle plastics from LCD TVs in a closed-loop system, it is first of all important to understand the compatibility of all plastics present in LCD TVs. In case of LCD TVs, most plastics are only compatible to a limited extent. Therefore, plastic should be separated with at least a purity of 98%, or impurity should be diluted to below 2% to be able to closed-loop recycle plastics containing flame retardants. Once the compatibility of the present plastics is known, it can be evaluated whether different plastic separation processes can achieve the required purity. To do this, different experiments were set up, which indicated that post-shatter separation based on density is impeded by the overlap in densities of different non-compatible plastics. Besides density-based separation techniques, also optical separation techniques such as NIR, XRT, and XRF were evaluated. Unfortunately, also these techniques proved to have a limited separation efficiency for post-shatter residue. This is due to the high concentration of black plastics. Based on the tested separation efficiencies and the measured density distributions for the plastics present in LCD TVs, the yield and purity that could be achieved for separating PCABS with phosphor-based flame retardants is calculated. These calculations show that only a yield of 71% and a purity of only 79% could be achieved, which indicates that at least a factor 10 dilution would be required to closed-loop recycle the plastics that could be obtained by this process. Besides experiments to separate plastics containing flame retardants after shedding, also multiple experiments were performed to recycle plastics after manual disassembly. Within these experiments, different options and technologies to identify and sort the disassembled components were evaluated, and the feasibility of closed-loop recycling plastics after manual disassembly was demonstrated. This was done by going through the entire process of disassembling backovers of LCD TVs, identifying the plastics type, sorting the components based on plastic type, sieving the plastics after melting, regranulating these plastics, and afterwards injecting molding the recycled plastics into a new backover, which was made from 100% recyclates and which was tested by TP Vision, the flat screen development site of Philips. Based on all these experiments, it can be concluded that post-shatter recycling of flame retardant plastic still requires several technical challenges to be faced. While the economic viability will remain uncertain due to the required investments and the low quality of recyclates that can be achieved by post-shatter recycling processes. On the other hand, performed economical analysis demonstrate that recycling plastics after manual disassembly is economically viable under the current boundary conditions. But for these processes to be industrially implemented, markets for recycled plastics with flame retardants will need to be developed. I hope this short presentation inspired you and that you will enjoy reading the article. If you have any questions or remarks, please do not hesitate to contact me.